Hello everyone, this is the Space Channel. The theory of relativity is a fundamental physical concept that has become a prominent symbol of science in popular culture. Contrary to the widespread misconception, it does not say that everything is relative. It says that all relative processes in the universe rest on absolute principles. The laws of physics operate the same everywhere. The speed of light is constant in the ultimate limit, and we all live in a four-dimensional space-time. The theory of relativity was formulated by the German scientist Albert Einstein to resolve contradictions in physics created by the combined legacies of Newtonian mechanics and Maxwell's electromagnetism. At the heart of those contradictions lay the behavior of light. By the late 19th century, visible light was both well understood and utterly mysterious. Centuries of work have revealed its source, explored how it spreads, and measured its speed with impressive precision. After James Clerk Maxwell's explanation of electromagnetism, it seemed that physics had closed the case. Light is an electromagnetic wave traveling at almost 300,000 kilometers per second. Yet that full stop soon turned into a bold question mark when scientists compared light as an electromagnetic wave with mechanical waves. If an ocean wave travels through water and a sound wave travels through air, through what medium does an electromagnetic light wave propagate? To answer, scientists proposed a simplifying hypothesis. Light moves through an invisible substance called the ether, but if the ether really existed, it should influence light's speed. Countless experiments with light beams showed instead that light always travels at exactly the same speed. Two radically new ideas followed, both clashing with the physics of the day. The ether does not exist, and light can behave not only as a wave, but also as a particle. Albert Einstein was destined to be the scientist who explained these paradoxes with a new physical theory, and, remarkably, the ancient Pythagorean theorem played a key role in his discovery. One evening in the spring of 1905, Einstein, then a humble patent clerk in Bern, boarded a tram on his way home after a long day. He often finished work quickly so he could ponder the universe in his spare time. On that ride, he devised a thought experiment that would change modern physics forever. As the tram pulled away from a clock tower, Einstein imagined the car moving at the speed of light. If he were traveling at 300,000 kilometers per second, the tower's hands would appear frozen, even though he knew they would keep ticking normally on the tower itself. Time had slowed for Einstein. The insight stunned him. The faster you move through space, the more slowly you move through time. How could that be? Einstein's thinking was shaped by two pillars of physics. First were Isaac Newton's laws of motion, which insist that velocities are always relative, never absolute. A train, for example, moves at 40 kilometers per hour relative to someone standing still, 20 kilometers per hour relative to a second train moving the same way at 20 kilometers per hour, and 60 kilometers per hour relative to a train coming the other way at 20 kilometers per hour. The same principle applies to Earth, the Sun, and even the Milky Way. Second were Maxwell's laws of electromagnetism, which showed that an electromagnetic wave such as light travels at the fixed speed of 299,792,458 meters per second, no matter who observes it. Yet that absoluteness seems to clash with Newton's relative velocities. If Newton's laws are universal, why should light be the exception? Einstein illustrated the conflict with another famous thought experiment. Imagine him standing on a railway platform while lightning strikes equidistant points on either side. Because he is exactly midway between the strikes, the flashes reach him simultaneously. For someone on a train hurtling past at near light speed, however, the flash from the bolt closer to them should arrive first if speeds were purely relative. Measuring different light speeds for the two observers would violate a fundamental truth of nature. Einstein faced a choice. Either Newton's laws were incomplete, or the speed of light was not a universal constant. He realized the two ideas could coexist if Newton's laws were modified just a little. To eliminate the mismatch in measurements, Einstein proposed that time aboard the train must slow down to compensate for the difference in the distances the two lightning flashes cover before reaching the observer so that the value of the speed of light remains constant. He called this effect time dilation, and he named his new framework the special theory of relativity. Newton believed time flowed at the same rate for everyone. Einstein, however, realized that time stretches and compresses, changing with speed. Because of this plasticity, time, like space, deserves its own dimension. In fact, he argued, the two form a single, four-dimensional fabric, a continuum called space-time, in which the everyday events of the universe unfold. Using the gravitational interaction between the more massive Sun and the lighter Earth as an example, Einstein suggested that the Sun does not tug on Earth with some mysterious force. Instead, it warps the space-time around it, and Earth gradually falls into that depression. Thanks to its orbital velocity, our planet does not crash into the Sun, but skims around the rim in an elliptical path. A simple analogy goes like this. Imagine a trampoline as the fabric of space-time. Place a bowling ball in the center, the Sun, and it dents the surface into a cone-shaped well. Now set a light ping-pong ball on the trampoline. If you merely drop it, the ball rolls straight toward the bowling ball. But if you launch it along the rim and keep nudging it, the ping-pong ball circles the bowling ball the way Earth orbits the Sun. To avoid plunging into a massive object's gravitational well, lighter bodies must reach a certain speed, either to stay in orbit or to escape the well entirely. Rockets do exactly that when they put satellites into Earth's orbit or send probes into interplanetary space. Earth itself travels around the Sun at roughly 30 kilometers per second, fast enough to counter the Sun's gravity and keep from falling onto its surface. Einstein called his framework a theory of relativity because it modified the rules of relative motion, which had long been used in Newtonian mechanics, where motion is always relative to the chosen frame of reference. He had to adjust Newton's relativity to make sense of a puzzling experimental fact. One phenomenon, the speed at which light propagates, is not relative at all, but absolute. From this emerged a new physics in which, at extremely high speeds, time slows, objects contract, and their mass approaches infinity. The special theory of relativity, STR, published by Einstein in 1905, describes the laws of physics for systems moving at constant velocity in the absence of gravitational fields. It unites space and time and declares that the speed of light is the same for every observer, regardless of their motion. The best-known equation of STR is E equals mc squared. To derive it, Einstein imagined a body that emits a pair of photons. Restricting the problem to one spatial dimension, he examined the process in two frames, one moving with the body, where the body is at rest, and one moving at a small, non-zero speed relative to it, much like a spacecraft and a ground observer. He assumed the two photons have equal energy and are emitted in opposite directions, so the body's overall velocity does not change. Comparing the system's energy before and after emission and invoking energy conservation, he obtained change in energy equals change in mass times c squared. With the reasonable assumption that a body of zero mass has zero energy, the general relation follows. Energy equals mass times c squared, or E equals mc squared. Here, E represents energy and m represents mass. The general theory of relativity, GTR, introduced by Einstein in 1915, extends the special theory of relativity, STR, to describe gravity as the curvature of spacetime caused by mass. In GTR, gravity is not a force, but the geometric deformation of spacetime around massive objects. This framework also predicts effects such as the slowing of time in strong gravitational fields. A vivid proof that relativity really works and that it matters in everyday technology is the Global Positioning System, GPS. GPS can pinpoint a position only after its software corrects for relativistic effects. The satellites update their coordinate data so often that the required timing accuracy exceeds what classical Newtonian physics can deliver. Both special and general relativity act on GPS satellites. Special relativistic effect. Because a satellite moves rapidly in orbit, its onboard time runs more slowly, so its clock loses about 7 microseconds per day. General relativistic effect. The satellite feels Earth's gravity less strongly than an object on the ground, so its time runs faster and its clock gains about 45 microseconds per day. The two effects combine to make the satellite's clock run 38 microseconds per day ahead of a ground clock. The gravitational term outweighs the kinematic term, so without continual corrections, GPS would drift by roughly 10 kilometers every 24 hours. Einstein's equation E equals mc squared also guided the development of nuclear weapons. The idea of nuclear fission, which powers an atomic bomb, emerged from discussions between physicists Lise Meitner and Otto Frisch in 1938 in Nazi Germany. Trying to understand the forces that hold a nucleus together, analogous to the surface tension of a liquid drop, they applied Einstein's formula to check whether splitting was energetically possible. Frisch later recalled, "We both sat on the trunk of a tree and started doing calculations on scraps of paper. When two drops of water separate, they are pushed apart by electrical repulsion with about 200 million electron volts of energy." Luckily, Lise remembered how to compute nuclear masses and found that the two daughter nuclei would be lighter by roughly 1/5 the mass of a proton. According to Einstein's formula E equals mc squared, that mass corresponds to 200 MeV. Everything fitted. Finally, the most dramatic predictions of general relativity appear on cosmic scales. Black holes are born when a massive star collapses under its own gravity. And the expanding universe today is explained by the Big Bang. Both phenomena have since been confirmed observationally, cementing Einstein's theory as the cornerstone of modern astrophysics.